Hello, my name's Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering, and this is module 31 in my computer networks lecture series where I talk about symmetric encryption. Now, symmetric encryption is a fairly simple concept to understand. So a symmetric cipher basically uses the same key for encryption and decryption. That's what we mean by symmetry. And most symmetric ciphers used today are what are known as stream ciphers. And stream ciphers are very simple encryption schemes to implement. They're basically an exclusive OR operator where we take our plaintext message, we feed it through an exclusive OR operator to produce our ciphertext, and to produce the ciphertext, we exclusive OR the plaintext with some kind of scrambling sequence X. And stream ciphers are popular because they're simple, and because they're simple, they're fast. So remember that if we want to use encryption to protect traffic over the internet, we want to have security, yes, but we also want to keep up our system throughput, right? Like we still want our users to enjoy high bandwidths, high throughputs. And so any kind of encryption algorithm that we use on internet traffic needs to be very, very quick. And so encryption algorithms that are based on kind of fundamental logic operations that can be implemented, oftentimes using specialized hardware are extremely attractive. And so the simplest possible stream cipher just basically takes the key and exclusive ORs the key with the plain text message. So the scrambling sequence X is just set equal to the key. This is also the worst form of ciphertext, or this is the worst form of symmetric cipher because it's ridiculously easy to guess the key. All we have to do is look for some known text in the plain text message, maybe a name, maybe a common letter that occurs in English prose, and we can very quickly recover the key using something called a plain text attack. And I'm going to talk a little bit more about plain text attacks in a couple of slides. More commonly, the scrambling sequence is what we call a pseudo-random bit stream that is a function of the key. And so I'm going to write this scrambling sequence as X sub K, and the subscript K indicates that the sequence X takes the encryption key as an argument, or the scrambling sequence X takes the encryption key as an argument, or said another way, the encryption key is used to generate the scrambling sequence. And we call it pseudo-random because the scrambling sequence appears to be a random bit stream, but it's pseudo-random because it is actually generated according to a particular algorithm, which we're going to discuss next. So the stream cipher example I'm going to present to you is something that's known as a synchronous stream cipher. And so the way a synchronous stream cipher works is that Alice and Bob generate exactly the same scrambling sequence, XK, because they share the same key. And then Alice generates the ciphertext by taking her plaintext message and exclusive ORing it with the scrambling sequence. Now, Bob ensures that his copy of the scrambling sequence starts at exactly the same point in the file that Alice's scrambling sequence began. And then, as long as Bob's scrambling sequence lines up with Alice's scrambling sequence, recovering the plaintext message is very straightforward. It's essentially just another exclusive OR operation. So the plaintext message M is recovered by taking the exclusive OR of the ciphertext with Bob's copy of the scrambling sequence. The reason why this works is because the ciphertext C is equal to the plain text exclusive ORed with the scrambling sequence, And so this operation in the brackets, is what was performed by Alice. This extra exclusive OR operator is what is being performed by Bob once Bob receives the ciphertext. But you'll see that we just have essentially the scrambling sequence, exclusive ORed with itself. And any digital sequence exclusive ORed with itself is just always equal to 1. And as a result, this goes to 1, and we recover the plain text message. So again, super simple and fast to implement this stream cipher. The encryption operation is an exclusive OR, and the decryption operation is just an exclusive OR. The generating of the scrambling sequence itself is a little bit more complicated than just a single logic operation, but it is also very efficient to implement, particularly in specialized digital hardware. In most cases, the scrambling sequence is generated using some combination of linear feedback shift registers. And so I'm going to do an example of what that looks like. My example is going to use a very simple linear feedback shift register, but then I'll talk about how the simple example is basically extended for more state-of-the-art stream ciphers. Okay, here's an example of a very simple, perhaps the simplest possible, linear feedback shift register. So we have a 3-bit register. The bits are shifted in a right-hand direction, so they're shifted to the right. That's what I'm indicating by this arrow up here. And the output, the rightmost bit in the shift register, is equal to our scrambling sequence, or gives us our scrambling sequence. And so we refer to the state of our linear feedback shift register as basically just the content of the register. And that state is going to change as the bits are shifted. So as the bits are shifted and as the state of the feedback shift register changes, also the bits in our scrambling sequence change as well. So let's do an example. So let's say that we initialize our linear feedback shift register to have a state of 0, 0, 1. That means the bits are 0, 0, 1. And that means that since the furthest right bit is equal to 1, the first bit in our scrambling sequence is 1. Now to generate the next bit in our scrambling sequence, every bit is shifted 1 position to the right. So the 1 bit is shifted out and back using these feedback taps. And so the 1 feeds into this exclusive OR operator, gets exclusive ORed with 0. 0 exclusive ORed with 1 is 1. And so we have the bit of 1 being fed into the leftmost position. And then the other bits just move 1 position to the right. So after our first shift operator, we have the 0 bit shifted here, the 0 bit shifted here, and then 0 exclusive ORed with 1 shifted all the way around, and the next state of our linear feedback shift register is 1, 0, 0, and the rightmost bit is 0, so the next bit in our scrambling sequence is 0. So let's clean this up a little bit. One, 0, 0. When we want the next bit in our scrambling sequence, we shift the 0, the 1, and then we take 0 exclusive ORed with 0, shift it around, and so our next state is 0, 1, 0. And again, it's this sort of feedback tap structure. This plus operator represents an exclusive OR, and the 2 taps are the ones that select the value of the middle bit and the rightmost bit to feed into the exclusive OR operator. So the next state is 0, 1, 0, and the next bit in our scrambling sequence is 0. And so we just keep on doing this, basically. So the 1 is shifted over, the 0 is shifted over, we take 1 and 0, the exclusive OR 1 and 0, which is 1. The next state is 1, 0, 1, 0, 1, and then we have 1 in our scrambling sequence. Then we have the 0 shifted over, the 1 shifted over, 0 exclusive ORed with 1 is equal to 1. We have 0. Then we have the two 1s shifted over. 1 exclusive ORed with 0 is 1. So now we have a state of 1, 1, 1. The two 1s are shifted over. 1 exclusive ORed with 1 is 0. We have a scrambling sequence of 1. The 1 is shifted over, the 0 is shifted over, and 1 exclusive ORed with 1 is 0. And so we have 0, 0, 1, and our scrambling sequence is 1. So I sort of jumped ahead kind of quickly through those other shifts. Hopefully you understand the pattern of what's going on here. I wanted to jump ahead though because you will have noticed that at this point, the linear feedback shift register has wrapped around. So we started with a state of 0, 0, 1, and now we're back in the state of 0, 0, 1. And that means that the pattern in our scrambling sequence is going to start to repeat itself. And the number of bits before we start to see a repeat of the pattern is known as the period of the linear feedback shift register. In this case, it's 1, 2, 3, 4, 5, 6, 7 bits. And the period in general is equal to 2 to the n minus 1, where n is the number of bits. So in this case, we've got 3 bits, 2 to the 3 is 8, minus 1 is 7. And that is kind of a fundamental property of linear feedback shift registers, and is why we call them pseudo-random bit sequences, because up until we wrapped around, we did seem to have kind of a random looking scrambling sequence. 1, 0, 0, 1, 0, 1, 1. Seems kind of random. But once we wrap around, then we see a repeat of that exact same quote unquote random sequence. And so we want to have scrambling sequences that look as random as possible. So in general, we use much longer linear feedback shift registers. And in fact, the scrambling sequence is often a combination of several linear feedback shift registers, exclusive ORed with each other, sometimes interleaved and scrambled themselves before they're exclusive ORed. So there are many linear feedback shift registers used to generate the scrambling sequence for actual industrial grade stream ciphers. One remaining question also is, okay, this is all fine, but where does the key come in? How is the key involved in generating the bit sequence? Basically, the key is equal to the bit sequence that is used to initialize the linear feedback shift register. So we initialize the linear feedback shift register to a state of 0, 0, 1, and so this would be equal to the key. Basically, both Alice and Bob would agree to initialize their linear feedback shift registers with the same state. And so their scrambling sequence would essentially start in the same spot in the period of the pseudo-random bit sequence. And so in this case, the length of our key would be 3 bits. So if you find yourself working in the area of encryption and perhaps designing ciphers, which I think would be very interesting work, you cannot design a good cipher without understanding how ciphers are hacked, because you need to make whatever scheme you come up with robust to attack. And so what I want to do is talk about a couple of ways you can go about hacking a stream cipher. And the first way is basically what is known as a brute force attack. And a brute force attack is as the name suggests, just trying all possible keys and seeing which one works. Now, in the case of our previous example, our 3-bit linear feedback shift register, we actually have not 8 possible keys, 7 possible keys. Because the key 000 is never valid, because if you initialize a linear feedback shift register to all zeros, it never gets out of that state. And so there are only 7 possible keys. That's not very many, obviously. And so if we were using a stream cipher with this very simple linear feedback shift register, all Eve would have to do is just try all 7 possible keys and see which one results in a readable message. We foil this by using longer keys. So for example, many industrial encryption schemes will use keys that are 128 bits long. And sometimes students, like when you first see this, you're like, well, 128 isn't a very big number. But remember, this doesn't mean that there's 128 keys. It means that there are 2 to the 128 minus 1 keys. And so if we assume that a cipher takes 1 microsecond to generate, it would take 1 times 10 to the 25 years to try all possible 128-bit keys. So this is definitely long enough, certainly for modern computers. So brute force attacks, sometimes they work, but they tend to be confined to the domain of guessing really terrible passwords. So sometimes when hackers try to compromise the system, they will not use brute force attacks to try and guess encryption keys. They'll use them to try and guess passwords. And so they'll look for things like common swear words or permutations on birthdays or names of pets or things like that. And that's generally what people mean when they talk about brute force attacks. A more sophisticated and perhaps relevant attack for stream ciphers is something that's known as a plain text attack. And this is an attack that uses partial knowledge of the message being sent. So if we knew the whole message, obviously we wouldn't have to crack the cipher, but sometimes we have partial knowledge. We maybe know what what part of the message is. So for example, to use a computer analogy, many computers, including Microsoft Office actually, use XML files, and all XML files start with the same 3 or same few characters, right? And so we don't know what the rest of the XML file will look like, but we do know that it starts with a particular header. A more sort of historical example is during World War II, codes would often be hacked by eavesdropping not on very active areas of the conflict, but on very quiet areas. So for example, the Allies would station, and I'm sure everybody did this, but one espionage group would station an eavesdropper to listen to an outpost that never ever had anything to report, the quietest place in the whole war. And so the message that would be sent every day by that outpost would be nothing to report. And if you knew that they were saying nothing to report, you could then reverse engineer the cipher that they were using. And so quiet, very boring parts of the war were often used to crack the current codes being used. And so let's do a little bit of a simple example with this. So let's assume that we're using, I'll go back to red so we can see it a little bit better. Let's assuming that we're using the same 3-bit linear feedback shift register that I had in my example a couple slides ago. And let's assume for the sake of the example that a brute force attack isn't possible. 7 keys is just too hard for us to generate. But to help us, we have knowledge of the first 2 bits of the plain text. And so I'm going to represent the first bit of the plain text message as M0 and the second bit of the plain text message as M1. And as we're going to see, the advantage of a plain text attack is not that it often directly gives us the key, but it does narrow the search space that we need to use in order to guess the key. So rather than guessing all possible keys, plain text attacks will allow us to narrow things down to a subset of keys that we can guess much more quickly. Okay, to help with our example, I've reproduced how the state changes in our linear feedback shift register and what the corresponding bits in the scrambling sequence are. And I'll denote the first bit in the scrambling sequence as x0, the second as x1, x2, and so on. And the ciphertext, let's assume, is a string that consists of the first bit being C0, the second one C1, and so on. And the plaintext message M0, M1, and so on. Now, Eve is the one performing the plaintext attack. And so what does Eve know? Eve has access to all of the ciphertext, obviously, because she's been able to eavesdrop it. And Eve also has the first 2 bits of the plaintext message. Now, what Eve is going to do is use her knowledge of the plaintext message to actually recover the first 2 bits of the scrambling sequence. And we'll explain why that is important in a second, or how that helps Eve in a second. And so we're going to assume that the key used was 001, right? Eve doesn't know the key. This is what Eve is trying to guess. And so what Eve is going to do is she's going to take the first bit in the ciphertext and she's going to exclusive OR it with the first bit of the plaintext message that she knows. Now remember that the ciphertext is equal to the scrambling sequence, exclusive ORed with the plaintext. Exclusive ORed with the plaintext. And anything exclusive ORed with itself is just equal to 1. And so when we exclusive OR the ciphertext with the first bit of the plaintext message, the plaintext goes to 1, and the result is we just recover the first bit of the scrambling sequence. We have knowledge also of the second plaintext bit, and so we take the second bit of the ciphertext, exclusive OR it with the second bit of the plaintext, and then we get the second bit of the scrambling sequence. And in this case, we know that the first bit is equal to 1, and the second bit is equal to 0. And so now Eve knows that the first bit in the scrambling sequence was 1, and the second bit in the scrambling sequence was 0. So how does this help Eve? Well, Eve also has full knowledge of the design of the linear feedback shift register. Because remember, we assume that the knowledge of the algorithm is just out there, everybody knows it, and the only thing that's secret is the key. And so Eve can look at the scrambling sequence in the linear feedback shift register, and she will note that there are only 2 places where a 1 is followed by a 0. This occurs when we initialize the state of the linear feedback shift register to 001, or when we initialize it to 101. These are the only 2 states that will give us a 1 followed by a 0. And so essentially what the linear feedback shift, or what the plain text attack has done, is tell us not the actual key, but again to sort of shrink our search space. So now rather than having to try all 7 possible keys, which we assume is somehow just impossible for Eve to do because her computer's too slow, now Eve only has to try 2 keys in order to guess the right one. She needs to try 101 and 001. And that's in general how plain text attacks work. Again, they'll give us a little bit of knowledge about, they'll sort of shrink the number of possible keys because they give us a little bit of knowledge about where we are in the scrambling sequence. And because linear feedback shift registers repeat themselves, we can sort of take advantage of that knowledge. And we can we'll still at the end of the day have to try a whole bunch of keys, but a lot less than we would without the knowledge that we gain from this attack.